thank you. Pleasure to be here to give my first seminar to IRES on my work. I look forward to, I met a few of you. I look forward to getting to know the rest of you in due course. To spare or share. Okay. So agriculture is it has a huge impact on the global environment. It is, in some ways, you can argue, it is the largest biome on the planet. When we think about the world's biomes, we think about forests and grasslands and savannas and so on. But truly, if you look at the extent of agriculture in the world today, it is the largest biome, the area of land that we use for grazing animals or growing crops. And if you look at a catalog of global environmental problems and you ask what role does agriculture play in this, if you think about land use, agriculture is the largest user of land on the planet. If you think about climate change, nearly 20 to 30% of greenhouse gas emissions, CO2, methane, and nitrous oxide come from agriculture because of either cutting down forests, growing crops and applying fertilizer, methane emissions from livestock production, or paddy rice, and so on. With biodiversity loss, agriculture is the biggest driver of biodiversity loss. With birds, where we know the data quite well, 60% of the threats to birds is from agriculture. If you think about water use, agriculture is the biggest user of water, 70% of water withdrawals and maybe 85% of consumptive use of water. And finally, you think about water pollution, coastal eutrophication, essentially algal blooms that develop in lakes, as well as in like the Gulf of Mexico, hypoxia, predominantly because of phosphorus and nitrogen running off from farms. So if you think about global environmental problems, I mean, we typically think about industries, we think about transportation and so on, but agriculture is right there. At the same time, hunger continues to persist around the world. This is a map from the FAO showing the degree of undernourishment in different parts of the world. In Africa, some parts of Latin America and Asia, very high degrees of undernourishment, over 25% in some countries. And on top of this, people are estimating that we'll need even more food. Population is rising. People, especially in South and East Asia, are, as they getting more wealthier, increasingly eating more meat-intensive diets. This combination of population growth and increasing consumption, some people estimate that we need to double food production by 2050. And just last one, these estimates are based on an assumption that population will stabilize by maybe 9 billion, maybe 10 billion people. Just last month, there was a paper that was published in Science projecting that population increases global population increases might reach something like 11 billion by 2100, and with a high estimate of 12 billion. So this doubling might actually be an underestimate if that's true. Okay, so this dilemma of how can we improve global food security while at the same time reduce its environmental footprint is a major problem that a lot of people are addressing around the world. Okay, so who's this guy? Anyone know? Yeah, so this is Norman Borlaug. Does the name ring a bell? Yeah? Yeah, exactly. So he's considered the father of the Green Revolution. He's credited with having developed dwarf hybrid varieties of wheat, which are high yielding. He worked in Mexico. He was responsible not for just the scientific development, but he also was leading the introduction of these new species in India, Pakistan, and Mexico, and saw huge increases in productivity around the world. So Norman Borlaug had a hypothesis, and his hypothesis was that the best thing you can do for the environment in terms of food production is actually to increase productivity. If we say that agricultural extent is the biggest problem we have today, then the best thing we can do is produce more food on the land we already have. So increasing productivity is environmentally beneficial. So this is Borlaug's hypothesis. And here's another way of thinking about it. Let's say you had your land globally was divided into some natural habitats that have a lot of ecosystem services that you want to preserve. And let's say you have some low yield farmland and high yield farmland. So this is your current state, let's say. And we have different choices on how to produce more food. One way is what people might call land sparing. This is the Borlaug hypothesis, which is let's increase the extent of high yield farmland, decrease the extent of low yield farmland, essentially increase the intensification of agriculture, produce more from the land we have, maintain natural habitats in the same extent. The other hypothesis, or the counterpoint to that, is some people call wildlife friendly farming or land sharing, which argues that intensive agriculture is extremely harmful to the environment, and so we want to expand this kind of wildlife friendly farming, which of course means this is low yield farming, so you'll need more land in use, and so it reduces the amount of natural habitat, but people argue that this is actually better. Okay, so this is a contrast between two different ways of producing more food. A report, this term land sparing, I was trying to find out who first coined the term land sparing. It was hard to track that down, but there was a report published by Wagner, a report titled "How Much Land Can 10 Billion People Spare for Nature?" And Wagner demonstrated his idea by showing Indian wheat area over time. So this is from 1961 to 2013. This is the area of wheat in India over time. Okay, so this is the actual data. This is the area that was used for wheat production in India. But over the same period of time, yields of wheat increased. So wheat production increased a lot more than area did. So if you ask how much area would you have needed if yields had not improved over time, that's the amount of area you would have needed if you had seen no yield improvements. So Wagner's idea was saying this is the amount of land we spared for nature by increasing yields over the 40-year time period. And so Wagner actually argued that the best way to produce more food and the least environmentally efficient way was to actually intensify production on the best agricultural lands we have. So essentially, identify what are the best lands, intensify production there. We actually can spare land for nature. That was a thesis of his report. Okay, and he was actually arguing that in fact, if you use marginal agricultural areas for agriculture, we might actually increase the environmental problem. We can do the same kind of thing for globally. That was just for India. If you look at 1961 cropland, globally for 6 different crop groups, this is what happened between 61 and 2004. We didn't increase cropland area very much. We mostly improved food production by increasing yields. However, if yields had not changed, we may have used twice as much land for agriculture. Okay, so this is a powerful argument in some ways, but there have been a couple of major criticisms of Borlaug, and that's the thesis of my talk today. So one major criticism is what people call Jeevan's paradox. People know what the Jeevan's paradox is? No? This is the idea that is what some people call the rebound effect, right? So let's say we improve the fuel efficiency of cars. Does it mean you actually decrease fuel consumption? No, people will drive cars more, or people who used to bike might now go and buy a new car because cars are more fuel efficient. I know some people who did that actually, personal colleagues who went and bought hybrid electric cars who previously did not have cars. So there is truth to this kind of behavioral response to improved efficiency. So the same thing could be argued for against Borlaug's hypothesis as well. When we have new innovations and produce more food, it doesn't mean that it might mean that we will consume more food, right? The other option, or the other criticism, is that land sharing is actually a better option for the environment. High intensive agriculture, even though it uses low amounts of land, is actually, because of the intensity of production, it's even more harmful for the environment. So in the net, some people argue, even though land sharing or wildlife friendly farming, you can see from the use of the term wildlife friendly, they assume that even though agriculture takes up a lot of area, it is more wildlife friendly, and in the net you're better off by having low intensity agriculture over a larger area. So we'll examine both of these today. First, the Jeevan's paradox. The argument against Borlaug is that Borlaug assumes a fixed demand for food. So Borlaug assumes that food demand is fixed, it doesn't change. However, whenever there's an innovation, as we talked about with fuel efficient cars, typically prices drop and people will change their consumption. So for example, one example I like to talk about a lot is coffee. Like, demand for coffee is not fixed. North Americans didn't drink much coffee, and then Starbucks came in, and now we drink a lot more lattes and cappuccinos, right, than we used to. So demand can be created, and it's not fixed. And typically, there's a response to price. So typically, when there's innovation, prices drop, and when prices drop, demand can increase. So several people have looked empirically on whether there is this kind of G1's paradox response or a reborn response. And one classic study that a lot of people cite is by Angels and Kaimowitz. They were from C4 in Indonesia. They did a case study of several different, I forget how many case studies, it was part of a book. They looked at a huge number of case studies of deforestation in the tropics, and they found that typically when there's new innovation, people end up actually expanding deforestation. There's more deforestation with innovation. The argument being that there is new innovation, farmer sees and farmer adopts it, the neighboring farmers see this innovation and this the adopted farmer doing very well, they continue adopting those practices. And so innovation actually spurs more deforestation, not less deforestation. That was their argument. This was analyzed globally by Tom Rudell and colleagues in a paper published in PNAS, so a very influential paper. And their hypothesis was that, before I show you that graph, essentially they were arguing that if agricultural yield increases cause land sparing, then if you just look at data around the world, you should be able to see coincident increases in yield and decreases in cropland area. That was their hypothesis. That was what they were looking for. So they said, let's look at yield increases over the last 30 years or 40 years and see if those yield increases were accompanied by decreases in area. Okay, was land actually spared? And this is the data. This is trend for 10 different crops for a bunch of different regions from 1990 to 2005. And in this column, you have two different numbers. The first is percentage change in yield. Okay, so these are all positive. So globally, everywhere in the world, we had positive increases in yield. And the second column, the second number here is changes in land area over the same time period. And what they have put here is whether there's land sparing observed. So if you have yield increases and decreases in area, that would denote land sparing. And you can see that for all but two regions, there is no observable regional land sparing. Okay. And in fact, what's interesting is if you take the two regions which had the highest yield increases, East and South Asia and Central Asia, with 40%, over 40% yield increases over this time period, they did not have land sparing either. Okay. In all these places, land area went up. What do you think? Yeah. You answered the question I was about to ask. So I was going to ask, what problem do you have with this analysis, right? The problem with this analysis is exactly that. This is it's a wrong hypothesis. Over the same time period, population has been going up, demand has been increasing, and so to really look at land sparing, you should be asking not whether areas increased, but whether areas would have increased even faster otherwise, right? So areas would have been increased just because demand is growing up. And so it's a wrong model. They didn't have a counterfactual, essentially an alternate world scenario where the green revolution did not happen. So they were looking at this data empirically without thinking about a counterfactual scenario. And this is a problem with a lot of analysis globally, in fact. So the two problems. One, first of all, is that this is also the Angelson and Kaimowitz case study work was regional, not global. So maybe, yes, farmers see this innovation happening in, say, Brazil, and neighbors adopt it, and they expand soybean production, let's say. But it's possible that if you look at North America or Europe, soybean production is dropping, and globally, land may have been spared elsewhere. Right? That's possible. They didn't look for it. They were just looking at regional case studies. So this is a good example for why sometimes regional case studies are not sufficient when you're thinking about a global problem like land sparing. So land sparing could have occurred elsewhere. They did not look for it. And the second problem is what Hisham just identified. They didn't have counterfactuals. They were asking the wrong question. You need to ask, would land sparing have occurred if compared to a non-green revolution world? So how do we address this empirically? It's really challenging to address this empirically because we don't have a controlled world where the green revolution didn't happen. And so we have to resort to models. So I'm not going to tell you about this model, but this is where I had a collaboration with an agricultural economist from Purdue University. So the interesting thing was I conceptually talked about these problems in an op-ed that Janine and I wrote in an ecological magazine. We conceptually discussed it, but we didn't know how to deal with it. Right? We knew there was a counterfactual problem. We knew there was this regional global problem. Turns out that my colleague from Purdue University had published a paper with this model in an actually he hadn't published the paper. He submitted a paper to the Agricultural Economics Journal, and they rejected his paper because they said, oh, economists already know this. It's not new. So he couldn't publish it. So I sent him the editorial, and he sent me this submitted paper. He said, here, you can read more about it. And it was great. I was like, wow, land use scientists would love to read your paper. Unfortunately, ag economics thought that it was not interesting. We ended up collaborating to write a paper that was more accessible to non-economists, and we managed to get it published in PNAS. So here's an interesting example of how sometimes disciplines, what one discipline thinks is interesting or not interesting can be extremely interesting to another. So we used this simple model, and we tried to ask this question. Essentially with this, let me just talk about the model a little bit. The model has three inputs. It has income per capita, which is fixed. So we have historical income per capita. We have historical population fixed. And we also have shocks to the productivity or yields, essentially either from investments, something like the green revolution, for example, or even could be climate change, although we didn't look at that in our particular example. So one of the caveats is that we in the model, we kept income and population fixed when we are examining this. So in a real alternate world scenario, we could also imagine that if the green revolution hadn't happened, global population today might be different, okay? Or global incomes might be different. So we didn't have that in this particular version of the model. I don't quite know how we want to do that without complex demographic model. So the model has price embedded in it. So as and how people will respond to changes in price. So as innovation happens in the model, there's more increased production, prices drop, and demand for food products might increase because of the price drop. And we have 15 different regions in the world, and it's essentially calibrated with data, historical data on how demand and supply responses shift. When there's greater demand for food, people can produce it either through increasing land or non-land. Okay, so people can either increase by expanding land or through adding more inputs. And again, that's calibrated through data that we already have. So enough about the model. How well does the model do? And this is showing just a kind of a validation of the model. The blue bars are actual data. The green, what I call real world, is what the model actually simulated. This is output, so total production change. So these are all changes over the last 40 years. So model predicts both output increases, area increases, yield increases, and price decreases over the last 40 years fairly well. Okay, it's fairly good. Essentially, most of the food production over the last 40 years came from yield increases, not through area increases. And price of food, real price of food, has dropped over the last 40 years, except for a couple of price hikes. If you look regionally, we don't do so well. So we have 15 different regions in the model. We aggregated those into green revolution and the rest of the world. And we don't do as well as we did globally. The output increases in green revolution regions are underpredicted, overpredicted in the rest of the world, and so on. For yields, we underpredict green revolution, overpredicted in the rest of the world. Okay? But the model, even though it's not perfect, gives you a tool to kind of explore this idea of a counterfactual scenario. Okay, so forget the blue curve now. Let's now look at this counterfactual scenario that we ran. So this is a counterfactual we ran in the model where there's no more innovation anymore. There's no green revolution. Okay? And so we have to now compare the real world scenario against this no green revolution scenario. Let's just zoom straight into area. So this is what the model predicts would have happened to area without a green revolution. We would have expanded agricultural area even more compared to what actually happened in the real world. Okay. That's the model output. So these are both now model outputs. Yes. So these are both model outputs now. They're a model real world, yeah. So there's the actual, that was the blue. That's the actual data. But when you want to compare two simulations from a model, you want to compare model to model. You don't want to compare model to, yeah. I can talk more about that later, yeah. I actually changed it to real world because it was more confusing with, we had a different term called baseline, but anyway. So think about the real world is what actually happened in the model, and the green revolution is what is a counterfactual that did not actually happen in the real world, okay? So both area and yield have increased in both scenarios, and this is because demand has increased over the last 40 years. But what we really need to look at is compared to this counterfactual, this is the amount of land area that was spared from agriculture because of yield increases. So yield increases in the real world were higher than would have happened without a green revolution. Okay, and you look regionally, you see compared to a regional outcome, compared to a real world, compared to a non-green revolution world, green revolution regions would not have expanded area as much. And in fact, in the rest of the world, Europe and North America, we've actually decreased cropland area compared to a no green revolution world where we would have expanded cropland area. So there's responses between in the green revolution world compared to the non-green revolution world. So I can bore you with a lot more details, but the bottom line from this is two things. First, historical green revolution was land sparing, at least within the framework of our model. Okay. So we really, if you use a counterfactual and think about what would have happened, historical revolution, historically we used less land than we might otherwise have. The second thing is we have to talk about a couple of caveats. First, we only considered one kind of innovation, just technological innovations. I would go into the details, but we essentially changed something called total factor productivity in the model. That's the only thing that happened. There are a broad suite of other innovations that may not have similar effects. The second thing is we found that with our model, and I'm not going to go into the details, we can lead you to the paper if you want. We did some future scenarios as well, looking at, okay, how might this work if you looked at a future green revolution? There's a whole bunch of people who are calling for a second green revolution in Africa, right? Africa is the continent that got left behind by the green revolution. So we did some future simulations, and we found in the model that this conclusion that historical green revolutions were land sparing is not guaranteed for Africa in the future. And why is that? In the paper, we did some theoretical analysis asking under what conditions would Jeevan's paradox actually happen. And it turns out that Africa meets those conditions today. So Africa, uniquely in a situation, there's a bunch of 5 conditions that need to happen, and Africa uniquely happens to be in a situation where if innovation happens in the future in Africa, it may not actually be land sparing. It may actually have increased land area expansion and maybe more carbon emissions. So that's something to keep in mind as we think about this. Okay, so Jeevan's paradox check. I would say, at least with this result, we say that Jeevan's paradox is not generally relevant for the green revolution. Green revolution did spare land for nature, maybe not guaranteed for Africa. Now let's turn to the other question. Okay, so we've now shown that maybe land sparing does happen, but even if it does happen, maybe land sharing is the better option for the environment. Okay. So this is an argument that came from a paper published in Science by Green and other colleagues from the UK, and they posed this question: what is better for biodiversity? Is it better for biodiversity to have a lot of agriculture that is really low intensive, or is it better for biodiversity to have very high intensive agriculture in very small areas? Okay, so these are two different hypotheses. And so they developed a theoretical model to think about this. And so you can imagine a situation where you have these are all unitless. Okay, so let's say you have a target production of 0.2, and you can achieve that target production of 0.2 either by taking a unit of area and farming very intensively with a yield of 1 on 20% of the area, okay, or you can farm 100% of the area with a very low yield of 0.2. Okay, so these are two alternatives. This is the land sparing alternative. So you farm intensively, but only in 20% of the area. You're leaving or sparing all of this for nature. This is the land sharing alternative, very low intensity farming, but covering the entire landscape. There is no more unfarmed area. Okay? So these are two different hypotheses. Which is better for biodiversity? The total impact on biodiversity. Clearly, in this farmed area, the 20% area that will be worse for biodiversity because it's high intensive production. But at the same time, you're leaving a lot of land for nature, right? So you really need to look at both places to think about what's in the sum better for biodiversity. So this is what they did. They hypothesized. They came up with two different ways of looking at it. So let's imagine that this is the high yield farming. This is a low yield farming. Let's assume. So this is a curve that shows, in this case, relative density. What they call, it's a measure of. It could be any measure of environmental quality, but in their case, they were looking at species richness as a measure of biodiversity. Okay. So let's say this is a biodiversity response to increases in yield. Okay, so this is a curve where as yield increases or intensification increases, at low yield, very high biodiversity, and as yield increases, biodiversity decreases according to this function. Okay, so it's the same function for both of them. So if you, in the unfarmed areas, you'll have a relative biodiversity of 1. In the farmed areas, you would have a biodiversity right here, because yield is 1. So you have a biodiversity of something like 0.1. On the other hand, if you had your entire area farmed with a yield of 0.2, that's the yield of 0.2, that would be your relative density, that would be the biodiversity. Okay? Yeah? That's correct. Yeah. That's yeah. So yes, there could be. So they are assuming that the world is separated into these halves, and that is one of the criticisms of this model. The many criticisms of this model, and one of them is this kind of off-site impacts. Absolutely. So then they said, so let's now sum up the total amount of biodiversity. So the biodiversity in this patch of land would be, because it's unfarmed, would be 1 times 80%, while the biodiversity in this piece of land would be 0.2, because 20% of the area times that value of biodiversity, so it would be that. While in this patch of land, it would be essentially that biodiversity over the entire area. So you can sum them all up. Okay, you can unfarmed and total farmed, and this would be the total population size in the highest yield farming case, and this would be the total population size in the lowest yield farming case. So this is just a theoretical model. Okay, so in the theoretical model, what this model is saying is that if the shape of the biodiversity response was like this, was kind of, I always forget whether it's convex or concave, but anyway, it's that way. It's convex, I think. Then you would have land sharing is a better alternative, because you have the total amount of species is higher than in the land sparing case. With me so far? Yeah. Good question. It doesn't ask which species. So, yes. So you can ask how would different species respond, right? I'll get to that in a couple of minutes. So you can ask, okay, what do they actually, this is a theoretical model. It's not asking what the species is. It's asking what if a species did this versus what if a species did something else. And then you can ask, what do the species actually do? Fair enough? Okay. So then the other thing is a species might do something different. A species might do something completely different from these two models, and that also shows up. Okay, species sometimes go up and go down. So then they go into the field and actually ask what is actually going on. So I'll get to that in a few minutes. So if you had a curve that was different, convex or concave, whatever it means, if the shape of the curve was this way, you get the opposite result. You can work through this later, but you get the opposite result where land sparing is preferred. You get more species this way. So essentially, you have two hypotheses: the biodiversity versus intensification. If the shape of the curve is like that versus the shape of the curve is like that. If the shape of the curve is like this, it favors land sparing. The shape of the curve is like that, if it's land sparing. If you hate the math behind all of that, another simple conceptual way to think about it is, in this case, as soon as you do a little bit of intensification, biodiversity drops dramatically, right? And so if you are in this shape of the curve, the biodiversity, let's say you have low yield farming, which would be somewhere here, the biodiversity between low yield farming and high yield farming is not very different, because it's kind of flat here. The big difference is what happened in the first instance. As soon as you go from 0 intensity to very low intensity, your biodiversity drops. So the best thing to do is to have very little land in high yield farming, because it's not very different to have from here, and have a lot of land preserved for nature. On the other hand, if your biodiversity drops like this, there's not a lot of difference between this and that. So you can have a lot of low yield farming with not much drop in biodiversity. Okay? Yeah, Kai. Yeah, I'll get to that in a second. Yeah, so they do find species that do all kinds of other things, right? So that's the next study. So then they went out in the field and they started doing some empirical work. And so this is a paper published by Ben Phelan in Science, where they looked at birds and trees. And so this pigeon, for example, as soon as intensification increases, its density drops dramatically for this pigeon. Okay, so it's a loser, and this pigeon would prefer land sparing. Okay, and this is another warbler where it does that, and in fact, it's also loses, but land sharing is better. This warbler would prefer a land sharing mode of agriculture. On the other hand, there are some species that win. They love agricultural landscapes, right? So you can have species that do that, and again, that's a winner. Again, you can work through the model. If the winner had this kind of shape, land sparing would be better. The winner had this kind of shape, land sharing would be better. And they had a whole bunch of species which, as Kai and you asked, that do all kinds of other behaviors. They go up and go down. Okay, so what they did was they went out and looked at different landscapes, and they looked at birds and trees, and they asked what curves do they fit. Okay, so that's their model. So here are 4 different options. You have winners or losers, basically species that love agriculture, that don't love agriculture, different shapes of responses, sparing, sharing best, sparing best, sharing best. Okay, so what did they actually find? So they measured trees and birds and trees in India and Ghana. That's where they did their field studies. So first of all, each of these show the proportion of species in different categories. So the pink ones mean this many species, like forget 0.01% of the species did this curve. Another that much species did that, and so on. The gray ones is where they didn't meet any of them. So you could say that maybe a third to half of the species didn't actually match any of these curves. Okay, their behavior was more complicated than these simple curves. But what's really interesting is that the biggest proportion here is all in red, which means the biggest proportion of species followed this curve, where their densities dropped really fast as yields increased. And so they're empirically, okay, now you have lots of caveats, only looking at trees and birds, and only looking at India and Ghana. But with this preliminary analysis, you would say that if you chose land sparing, you would protect the most number of species. Yeah. Can you? Yeah. 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 I think I might need to talk to you afterwards to make sure I'm understanding your question properly. But so in both models, you are encroaching into the forest, right? Both the land sparing and land sharing model. In the land sparing model, you are encroaching into the forest, but you're actually sparing more land for forest. You're taking the existing land you have and intensifying production. In the land sharing model, you're actually you are encroaching into the forest, but in a very low intensive way. So you're using land in both cases, but in one you're protecting, you're setting up more protected areas. And correct, yeah. In the land sparing model, yeah, yeah. Yeah. So, these curves are actually empirical, right? So they go out and measure it based on different intensities. So they're going out in the field and they're asking how many species exist in this agricultural land versus that agricultural land versus a protected area. So that's an empirical. That's what's actually happened. That's what's going on already. And what this is actually saying is that this first big drop as you increase yields is actually quite critical. In some ways, it's supporting what you're saying. Is that you would support a land sparing model, which is saying let's set aside a lot of land. Yeah. Yeah. No. That's a good point. Yeah. Hmm. That's a good point, Kai. I have a case later with soil fertility where I have a similar problem with the humpback, okay, I'll talk to you afterwards. I think it might be useful to go back to their paper and see what their data actually shows. You had a hand up earlier. Okay. Yeah. Okay. So the point of my study was actually of my talk today is to say, but all of this is this intense debate about Phelan. There's been responses back and forth, but they're all focused on biodiversity. They're concerned about one environmental problem, which is biodiversity loss. But as most of you know, there's a whole bunch of other environmental problems that we are worried about. Is it better to land spare or land share? How can we know that? So one of the things I've done is to just do a brief review of okay, let's look at other problems, see how it works out. Okay, and maybe we can use the same kind of model. We can adopt the land sparing model for biodiversity and try to apply it elsewhere. Yes. I believe it's just the incidence. I don't think they looked at rate of change because there was a couple of different field visits, from what I understand. Yeah, but yeah. So, and that's a good point actually. It's not clear when they are thinking about biodiversity whether it's an equilibrium biodiversity or when they're not looking at they're not looking at the land use history, like how long has it been, because it takes time for biodiversity to, that's a really good point also. So let's think about greenhouse gases. So we thankfully for greenhouse gases, there's a study that looked at this, that looked at, okay, what would have happened if there had been no green revolution, okay, with greenhouse gases. So this is a real world scenario. Again, it's like the economic model I talked about, but with, running out of time. So this is a real world scenario. There are 4 different curves here: soil emissions, fertilizer production, rice cultivation, so that's methane, and land conversion. So this is the emissions from CO2 emissions from converting land. So this is what actually happened from 1965 to 2000 something, I think. And then they looked at a counterfactual scenario, an alternate world where intensification did not happen. And if intensification had not happened, we would have cleared more land for agriculture. And so we would have increased CO2 emissions, but we would have decreased fertilizer N2O emissions from fertilizers. These are all scaled in terms of equivalent carbon dioxide equivalent. So compared to a counterfactual scenario, the current real world, we actually emitted fewer greenhouse gas emissions. So yes, it is a log scale, so by a lot. Yes. So essentially, another way to think about it is that if you intensify production, you're applying more fertilizers, you're increasing nitrous oxide emissions, but since you're using less land, you're decreasing CO2 emissions. So on balance, which one wins? Turns out CO2 emissions win compared to the increased CO2 emissions from land sharing is worse than the decreased nitrous oxide emissions. Okay, so that's a pretty simple. It makes sense. And so in this case, their argument is land sparing intensification was better for greenhouse gas emissions. Now let's look at another problem. Water quality. Okay, so this is from a study done by a former colleague at Wisconsin. This is nitrogen fertilizer application. This is maize yield. As you put more and more nitrogen into the land, yields typically go up, but then they start tailing off. So you have a diminishing returns in terms of yields. But leaching, the amount of nitrogen that gets left behind and gets washed into the groundwater, has an exponential response. It increases faster and faster, and that's because you're leaving, as you're applying more fertilizer, the ability of plants to take it up decreases. You're leaving more behind in the soil, so the amount that gets lost to the environment increases faster and faster. So this is a measure of water quality, right? You can think of this as water quality gets worse faster and faster. So if you take that curve and invert it, so the inversion of that would be water quality. So as you increase intensification, initially water quality is quite high. Initially, as you increase intensification, water quality doesn't get worse, but ultimately it crashes really rapidly. Okay, so I'm taking the same green model now and applying it to water quality. That shape of the curve suggests that you should favor land sharing for water quality. So if you're concerned about water quality, land sharing is a better model. You want to get rid of hotspots of high nitrogen use. You can ask about soil organic matter. What does the shape of the curve look like? And it turns out it's similar to what Kai talked about earlier. We get a funny thing. So as soon as this is from a paper by Matson, as soon as you convert from agriculture, from native vegetation to agriculture, initially you cut down forests, you plow the land, you start growing crops. That initial disturbance, you lose a whole bunch of soil organic carbon from the soil really fast. Ultimately, it stabilizes, and then in this particular case, this is from the Midwestern US, they went from conventional tillage to reduced tillage, and you actually start putting soil organic carbon back. And depending on the yields, if you actually increase the amount of yield in crops, you can actually put a lot of soil organic carbon back into the soil again with increasing yields. So the shape of the curve might be something like this. And as Kai said, if the humpback was like that, you would favor land sharing. In this case, both this end and that end are really good for soil organic carbon. Either undisturbed or very high intensive yields can both be potentially good for soil organic carbon that might favor land sparing. I need to think a little bit more about this model. But you can start to see that we can look at different environment problems, and you can see that you might get different responses. And so if you put those back into the green model, if you're worried about biodiversity, greenhouse gases, or soil fertility, maybe land sparing is a better option. But if you're worried about water quality, maybe land sharing is a better option. I think I'm going to skip a few slides. Maybe I should talk about this. This is from a PhD student of Janine, who's in forestry, Sylvia Wood. Her work shows in Peru. This is field work. This is looking at available phosphorus, or a measure of soil fertility. This is a measure of biodiversity. This is mean fallow length in this case, and years since initial clearing here for species richness. The biggest point I want to make is this is where the primary forest is. Okay, so doesn't matter what the fallow length is. Available phosphorus is not getting back up to what the primary forest is doing. Same thing here. Doesn't matter how many years has passed since initial clearing. Species richness is much lower. This is 200, so it's more than twice what we are seeing in different fallows. And this is field work in Peru. So the first cut seems to make a huge difference in these systems. I'm going to skip some of this stuff because I'm running out of time. Maybe just say that we did some some more modeling studies, and we looked at how much does baseline matter. I won't go into the details, maybe just talk about the conclusions. The difference between the baseline or the natural vegetation biodiversity and what you're putting it into makes a big difference. So if you're going from a natural forest, let's say, to an arable land, the baseline difference with going from a forest to cultivated land biodiversity is so huge that yields are more important and maybe favor land sparing. So then the yield difference is hugely important. On the other hand, if your baseline is very similar to cultivated, so let's say you're going from pasture to a natural grassland, or you're going from secondary forest to an agroforestry system, the baselines are fairly similar, then the difference in biodiversity between, say, sorry, skip the slide, between wildlife-friendly farming and, say, an intensive agriculture, the difference in biodiversity matters. So the context also matters. So our ultimate kind of conclusion, sorry, let me get through that, is that if you think about two different systems, think about tropical forests, and this, I don't necessarily mean all tropical forests, think about this as a placeholder for certain kinds of systems that are typically found in the tropics versus temperates, mosaics. In the tropical forest, we have a lot of intact forests today. Okay, this is where we have the biggest biodiversity hotspots. And this is where we are concerned about primary forest species loss and greenhouse gas emissions today. This is where deforestation is going on. We are worried about biodiversity loss. In a temperate mosaic, most of this land has been cleared a long time ago, North America and Europe. We don't have a lot of intact forest remaining. We are worried about losing cultural landscape species in these areas, especially in Europe. And the problem of concern is water quality. It's not greenhouse gas emissions or deforestation. So our concerns are very different. In terms of food, undernutrition is a problem in these regions. The problem we have in these parts is overnutrition, maybe obesity. We are producing enough food in these parts of the world. So maybe land sparing and land sharing lend itself to different places based on the problems of concern that we have today. So the final takeaway messages is, this is a term I coined last year. Land sparing may be the way to go. If any of you use this, you owe me copyrights. So the socio-ecological context is extremely important. We really need to think about the land use history. We need to think about what baseline are you converting from. We need to think about what species are you worried about, what environmental problem are you worried about. And this is, I think, something that actually Janine's work really got me to understand. The first cut seems to matter a lot. The loss in environmental quality at the first cut seems to be more important than what you do afterwards. And there are some people who have done some modeling studies that show that there is a crucial threshold, something like 30%, I think, at which you really rapidly lose your intactness of your forest and the environmental quality. So we need to really think more about this and not just hope that by setting up corridors and land sharing systems that we can gain our environmental quality back to the initial pristine state. And finally, whenever we hear about land sharing systems like Costa Rica, Kai, we're typically talking about agroforestry systems, shade-grown coffee, and so on, and they are great. But until we can grow rice, wheat, and maize with land sharing systems, I think we still have a problem, right? So the critique of land sharing is not that we shouldn't do it. It's that can we actually do this for all kinds of crops that we grow in the world? Can we get away with doing land sharing for rice, wheat, and maize? I'm not so sure. So I think my bottom line is to say it should be land sparing. We should think about what system we are working with. If we're thinking about producing maize, maybe not. We shouldn't be producing maize at all. But rice and wheat, we should be maybe using land sparing systems, and maybe coffee and other things where you can do land sharing. We should be adopting those. Thank you very much. Yeah. The yes, yeah, they include, yeah, they include cotton and yeah.
And then
So yes, so you mean when they talk about doubling of demand? So there are two different schools of thought. So one school of thought says you look around the world, we have food waste, and in some ways the food waste situation may be getting worse. And if you look around the world, people are eating more meat, and so the, we have to account for these in our future production. So they kind of assume that the world works the way it does. The other school of thought is saying we are already producing more food on the planet. If only we cut food waste, and if only we changed our diets, right? And I find that there's a huge dichotomy between these two groups. And yeah, some people think we don't need to produce any more food, and some do. Having said that, I think even if you believe that we can actually don't need to produce more food, or we can actually decrease food production, even if you think that, the land sparing and land sharing model is useful, because then if you want to think about taking land away from production, what's the best way to do it? Do we set aside more protected areas, or would we just have the amount of land we have today and de-intensify in different places? So I think that model is still applicable no matter how much whether you think food needs to be increased or decreased. Yeah. Yeah. Excellent, thank you. Uh, for your first question, there is a debate about that. There was a paper published by Eric Lambin that proposed a different model, which is when the price is right, we will bring more land into production. Yes, there's a theoretical limit, which is the amount of land we have, but if you think about Netherlands, they're growing poppy on reclaimed lands from the ocean. So when the price is right, I think people bring marginal lands into production, and by some arguments, that's actually worse for the environment. Yeah. The other thing is, yeah, there are two criticisms about the Borlaug model or the G1's paradox. One is that the sparing happens elsewhere, but there's also the issue of counterfactual. So land in general over the last 30 years has been expanding. The question we need to ask is would it have expanded even more? And if it had, yes, if you had run out of land in that particular scenario, we would have produced far less food. Would that have fed fewer people, or would that mean we would have reduced food waste? I don't know. That's a good question. Yeah. No, it has to be so great that it's counterproductive. So yeah. There's typically always a Jevons paradox. There is always a little bit of rebound. Yeah. Yeah. Yeah, that's correct. Yeah. Hisham? That's right, yeah. I mean, the Jevons, so this is, okay, so this is based on an understanding of what Jevons paradox is, right? So Jevons paradox is saying that the effect is so strong that it counterbalances. So, I mean, maybe remove the term Jevons paradox and say what we were testing is an alternate no green revolution model, right? And which innovation didn't happen, would it have used more land or not? Yeah. So, yeah. Okay, maybe I should have used a different term. Yeah. This is a term that my economist colleagues like to use, and I don't know if they embrace a different view of what it means. I don't know. So, Milan? Want me to flip back or no? This one? This one? Ah. Okay, so the model was calibrated to historical data. So there's only 3 inputs that go into the model. One is population income per capita, which is fixed, and total factor productivity, which is, yeah, that's correct. Yeah, yeah. Yes, yes. Yields are slightly lower, and prices are slightly different. Yeah. Yeah. Sorry. Oops. Do you think that bias would I mean, so here we are comparing 2 different models, right? I'm not comparing actual to model. So these are both model realizations. So the bias how does the bias in the model affect this result? Yeah, absolutely. Yeah, that the biases there's the same biases in both realizations. It's a huge hit. Yeah, absolutely. I mean, it was a huge hit on yields, right? Yields over 100 years for maize increased by 10 times or something, right? From 1 ton per hectare to, no, that's starting before the Green Revolution, but yields were at 1 ton per hectare, and now they are at 10 tons per hectare in the U.S. So, the other question I thought you were going to ask is why are these differences, and that partly has to do with the model's trade, how we calibrate trade. The model has to make assumptions about whether the market, whether it's a free market or whether it's a structured market. Leila? Yes. I mean, I Yeah, I mean, I think I see where you're going, but I also see some assumptions embedded in what you said. Like you're assuming that the Green Revolution didn't have benefits in India. Uh, so that, yeah, yeah, yeah. I mean, I see where you're going, but I think there are also different schools of thought there. I mean, so there is the Vandana Shivas of the world that think that the Green Revolution had, massive environmental and social consequences in India, and there's some truth to that. There are certain people who got left behind, but there are also people who believe that the Green Revolution lifted a huge number of people out of poverty. That, in fact, if you look at the data, India used to have more famines before, and we don't have those kind. I mean, we still have chronic malnutrition, but the kinds of famines that we had in the 60s and 70s don't exist anymore. So, like if I think about the industrial agriculture today, I look at the maize production system in the U.S. and I think that's ridiculous. Like we are, it's the biggest crop grown today, and very little of it actually goes to food. But I look at wheat and rice, and yes, there's a second and third biggest crop, and they do provide nutrition for a lot of the world. So I see where you're going, not generalizing too much, and we shouldn't be intensifying maize production systems probably, but we could be for other crops. Yeah. Yeah. I mean, one of the questions I really want to ask is, and I don't quite know empirically how to do it. I mean, I know rhetorically how to do it, but empirically I want to ask, did the Green Revolution actually feed more people? Did it actually lift people out of poverty? I don't know how one would empirically try to address that, but that would be a useful question to ask. And I think Vandana Shiva assumes, or her statements are that it didn't. And when I gave a talk at the LU a few weeks ago, and I presented sort of an overview of the Green Revolution, and I actually took some Prabhu Pingali, who's he used to be at the Gates Foundation. He was one of the people who worked at CIMMYT in one of the CG centers. He wrote a review on the Green Revolution, and he admits that the Green Revolution left a lot of people behind, especially women. It didn't address women's issues. It didn't. It obviously has huge environmental consequences. But it also lists some of the benefits of the Green Revolution, and I any counterpoints, counter arguments to that? Yeah. Thanks. I mean, the same kind of question came up at my last talk at the LU, and one of the things we talked about was the fact that subsidies in Europe and North America are probably the biggest lever we have to change some of the ways things work. The reason we are producing so much maize in North America is because of the price support schemes, and cotton and a whole bunch of other things, and lobbies that make sure that the next farm bill gets signed again, right? How we change that leverage, I don't know. Leila, I think this this is just the beginning of a long conversation, maybe, but I'll try to engage as I can. Where I now? No. Thank you.